In 1991, there was a huge volcanic eruption in the Philippines, known as the Mount Pinatubo eruption, which put huge amounts of aerosols into the stratosphere and caused the Earth to cool the next year by about 0.5 degree Celsius, or about 1 degree Fahrenheit on global average. But this volcano did not only affect temperatures, it also affected precipitation. And so in the Amazon and the Ganges-Brahmaputra basins, there was some of the lowest river flow rates ever recorded. And these low river flows have been associated with this volcanic eruption. And so people have proposed cooling the Earth through these geoengineering approaches, which involve intentionally putting aerosols into the stratosphere. And so we wanted to investigate, would the same kinds of relationships between temperature changes and precipitation changes occur for sustained aerosol loadings as occur in the relatively brief, approximately 1 year aerosol loadings that are a result of volcanic eruptions. And what we found was that the contrast between the land temperatures and ocean temperatures are established relatively rapidly. Say within a very small number of years, within a year or so, the land surface temperatures adjust and cool off more rapidly than the ocean temperatures. And this cooling of the land causes an anti-monsoonal circulation, or a tendency towards an anti-monsoonal circulation. So monsoons, in part, are driven by a warming of the land relative to the ocean, and so the air rises over the land, brings in cool, moist air from the oceans. And so if you cool the land relative to the oceans, you tend to inhibit these monsoonal circulations, which is one of the reasons why, for example, the Ganges and Brahmaputra basins are thought to have had less precipitation at that time. But the global mean temperature is largely determined by ocean temperatures. And ocean temperatures take several decades to adjust. And so you see relatively little change in ocean temperatures on the time scale of a year or even a small number of years. And so after a volcano, since the land-sea contrast is established rapidly and that inhibits the monsoonal circulation, you see a relatively large effect on precipitation, but because the ocean temperatures are largely governing the global mean temperature response, you see a relatively small response in temperature. So what we found was that for longer or more sustained perturbations to the climate system, that the monsoonal effect on precipitation stays about the same, but that the oceans start to cool off, and so you have a much bigger global cooling effect relative to the precipitation changes. And so if you look at Mount Pinatubo as an analog for, say, a sustained stratospheric aerosol loading, you would think that there's much bigger precipitation changes per unit temperature change from putting aerosols in the stratosphere. And while it's true that stratospheric aerosols will inhibit these monsoonal flows and inhibit precipitation on land, that the amount of precipitation change relative to the global mean temperature change is much smaller for sustained aerosol loading.